So we have a review for our second review for our chapter 1 section, the characteristics of functions. And the first part is identifying and locating the type of discontinuity that exists within each graph within this graph right here. So this type of graph has a removable discontinuity, and it's located at the x value of x is equal to -1. The second type of discontinuity displayed here, this is an infinite discontinuity. And this is located at x is equal to -2. Again, we can see that here, these two ends, these two again, are approaching infinity at that place where the graph is not connected anymore. And this one here is a hole. It's not connected because this portion of the graph is disconnected by this hole right there, but then still continues to this section of the graph. And that's referred to again as a removable discontinuity. So removable. Now the third type of discontinuity is a jump discontinuity, because the graph is not connected, it's not continuous, because it jumps from this open circle to that point right there. So this portion is graphed right here, it jumps up to that closed circle right there and then continues downwards. So because of that, this is referred to as a jump discontinuity, and that is occurring again at this value here on this line, which is 1, 2, 3 units to the left of the origin, so at x is equal to -3. And this again is from section 1.5. So the next section, 1.6, has to do with the end behaviors again of our graphs. So our end behaviors here on this graph, number 4, are both pointing downwards. So we describe these end behaviors as x approaches -infinity, which again is the left side, f of x is approaching -infinity. And as x approaches +infinity, which is now the right side, this right side right there, it is also pointing downwards. So f of x is approaching -infinity as well. If we look at example number 5, again, the end behaviors of this graph, one side is bounded, the other side is not. We're looking again at identifying how the ends of the graph are behaving. On the left end, as x approaches -infinity, this is unbounded and it's increasing again. So that's approaching +infinity, not negative, +infinity. As x approaches +infinity, notice that the graph is bounded, and it's bounded by the horizontal line y is equal to -6. So this graph behaves on the right side by approaching -6 from above, and it's not going to go below it. That's a similar thing is happening on number 6 as what's happening right here on this end of the graph, that on number 6, both the left end and the right end are bounded by the line of y is equal to -1. So both ends of the graph, the right end is bounded from above and is approaching -1 from underneath it, and the right end of the graph is approaching -1 from above it. But both ends again are bounded by that horizontal isotope. Now moving on to our next section, this again is symmetry. We need to determine the type of symmetry, again, the function has, and how that relates to whether we have a function, an even or an odd function at all. So the first one, because this is symmetrical through the y-axis, it is referred to as an even function. And again, these two things are synonymous with each other. If it's an even function, it is symmetrical to the y-axis and vice versa. Now, because this function is symmetrical through the origin, meaning that if I graph, let me trace over this. If I trace over this, Oh, it's going to be bad. Let me try that again. Let me zoom in. And let me trace over this as well as I can. Okay. And if I were to rotate this function, rotate this upside down and line it up again, I would notice that the graph again matches up exactly by rotating this 180 degrees. So if I rotate it 180 degrees and I can make it look the same, then it's going to be, again, symmetrical to the origin. So this graph is symmetrical through the origin, which implies then that this is an even function. So this is very important, again, that we recognize the characteristics of and the correlation between having a even function and how it correlates and what that means, and how that means it's symmetrical to the y-axis, and an odd function. I circled the wrong one here, my bad. And an odd function, and how that means it is symmetrical to the origin, and vice versa. So that's very, very important, again, to understand that because this is symmetrical to the y-axis, that for every point that we have here, we're going to get a point on the opposite side of this line that's going to have the same y value. So like right here, we see that the x value is 3 and the y value is 5. And we'll see that when x is equal to -3, the y value is also going to be 5. So that's really important, again, to remember that for every x, y, negative x, positive y is also going to be on the graph. And for every x, y here, the opposite x and the opposite y is also going to be on the graph. So understanding that and being able to test whether a function is even or odd will determine, again, the type of symmetry, or whether the symmetry is across the y-axis or the origin will determine, again, if we have an even function and an odd function. So again, it correlates exactly to that. And well, the last one is symmetrical through the x-axis. Notice that the top graph again matches to the bottom graph. So this is symmetrical to the x-axis. And because it's symmetrical to the x-axis, then more than likely this is not a function, which in fact is true. This one right here is not a function because we see that the x value is repeating at the x value at positive 4 is repeating. We have a 4, positive 3, and then we have 4, negative 3. So our x value repeats, so this is not a function. Let's look now at the back page. At our next page. For our next page, we need to determine if the relation is an even or odd function. Now, we can do this by one of two ways, by remember the shortcuts or by remembering what it means for a function to be even or odd. If a function is even, then that implies that for every x and y value, the negative x is going to have the exact same y value. In other words, that it's going to be symmetrical across the y-axis. That's what it means for a function to be even. So let's just check that out first. So if this thing is going to be even, then it's going to be symmetrical to the y-axis. So if I have my x's become a negative, and I simplify this, you see that I end up with the exact same thing. This becomes positive x to the 4th because multiplying negative 4 times becomes positive. That's an even number of negatives. So negative and negative is a positive. So and another negative times another negative is positive. And of course, x to the 4th is going to be x to the 4th. This, we still end up with a negative 3x to the square because right here we have to first raise this to the second power. This is a square, which again is a positive x squared. And multiplying that positive x squared with negative 3 ends up giving us negative 3x squared. And while the negative 9 stays as negative 9 because that's not going to simplify to anything. But notice again how this matches to the original function. These two things, again, are equivalent. And because of that, that means that this is symmetrical through the y-axis. And because it's symmetrical through the y-axis, that means that it is going to be an even function. So this is an even function. Now there's a shortcut that we can bypass. Instead of doing this substitution and using this test, we can use a shortcut with these type of functions because they have exponents by simply looking at the exponents. If we look at the exponents and all of the exponents are even, then it's going to be an even function, which is exactly what's happening here. Even the 9, even though it's not written, the 9 has an exponent. The exponent on the 9 is x to the 0 power. Since 9 doesn't have an x, that means it's x to the 0 power, and 0 is still an even number. So all of these exponents are even. Therefore, we can use that shortcut and not do this work in the substitution and determine that this is going to be an even function. So with that shortcut, that's going to make number 12 easy to identify, because here, instead of doing the substitution and checking if this is even or odd, we can simply look at the exponents, and because these exponents are both odd numbers, that means that this is going to be an odd function. Now the key thing in understanding this, however, okay, now that we know that this is odd, always go back and understand what that means, okay? Because we'll call this f, because f is odd, or the equation, because the equation is odd, or the function is odd, then the graph is symmetrical across the origin. This is going to be really important again in the next two questions. And being symmetrical across the origin means that for every xy that's on the graph, negative x and negative y is also going to have to be on the graph. And well, for number 11, in order to determine whether number 11 is even or odd, again, we would simply look at those exponents. Since here we have an exponent of 5, an exponent of 1, and this last value here, 1, doesn't have an x, that means it's x to the 0 power. And this exponent is even. So we have one even exponent and two odd exponents. So since the exponents are not all the same, even nor odd, this is going to be neither. This is neither an even function or an odd function. And which means it has no type of symmetry. No symmetry through the y-axis nor origin. And because it's a function, automatically it is not symmetrical through the x-axis. Functions cannot be symmetrical through the x-axis. So let's use that information and again the correlation between symmetry and even and odd functions to answer questions 13 and 14. Now, since on number 13 I'm giving you the fact that f is an even function, okay, let's again make the correlation with that symmetry. So because, this is the symbols that I use for the word because f is even, then the graph of f is symmetrical across the y-axis. And well, what does that mean? Well, what that means is then, because it's symmetrical across the y-axis, that implies that for every x, y that's on the graph, for every point that's on the graph, negative x, y is also going to be on the graph. And that's how we're going to answer this question. Since I'm giving you that f is an even function and I'm giving you this coordinate right here, f of negative 3 is equal to 12 means that the x value of negative 3 has a y coordinate of 12. So I'm giving you a point. So since this is a point on the graph, then that means that the opposite of negative 3, which is positive 3, is also going to have the y coordinate of 12, which is what I'm asking you to find. And that's how we get our value for f of 3. Therefore, f of 3 is going to equal to 12. And there's our answer. So for number 14, similar situation. If we look at this function, we have to recognize that this is an odd function because, again, by that shortcut, we have x to the third power and we have x to the first power. They are both odd exponents, so this would be classified as an odd function. So since, or because f is odd, then the graph is symmetrical across the origin. And well, why is that important? Well, because we now know again that all odd functions are symmetrical through the origin, that means that for every xy that's on the graph, the opposite x is going to give us our opposite y value. And again, I am providing that information for you. I'm telling you that f of 2 is equal to negative 4, meaning that we have the point of 2, negative 4 on the graph. So if 2, negative 4 is on the graph, then the opposite of 2, which is negative 2, is going to have the y value of the opposite of y. So our y value is negative 4, and we're going to get the opposite of that. So the opposite of a negative is a positive 4. So this point is also going to be on the graph, which is going to help us again answer this question and figure out the value of f of negative 2. So therefore, f of negative 2 is equal to positive 4. And there's your answer. Now, to find the average rate of change, the first thing we need to do again is figure out the corresponding y values for x is equal to negative 2 and x equals positive 1. So for negative 2, we're going to evaluate this, which equals 9. And then we evaluate our function with 1. Which equals negative 3. So the corresponding y values, the y1 value would be 9, and the y2 value is negative 3. So to figure out the average rate of change, we simply use our slope formula. y2 minus y1 over x2 minus x1. Which if I take this one value at a time, if I take the numerator first, that equals to negative 12. Take the denominator, that's equal to 3. And dividing this out or simplifying this equals negative 4. So there is your average rate of change. Moving on to our next example, number 16. We're going to find again the average rate of change. So we have the x1 value of negative 8 and the x2 value of negative 4. So we start by first plugging in each number into our function. So 2 times negative 8 squared minus 5 divided by negative 8 plus 1. And this equals first to negative 123 divided by 7. And now plugging in negative 4. equals negative 9. So of course you're going to get these values using again the function and just simply plugging those points in. So this just simply requires to making sure that we get the correct y values by correctly evaluating our function. Because if we end up with the wrong numbers, then even if we use this formula correctly, we're still going to end up with the wrong answer because these numbers are incorrect. So you have to make sure again that these numbers are correct in order then to figure out the average rate of change, which is again is just simply the slope between these 2 points. So getting negative 9 and subtracting negative 123 over 7 is divided by negative 4 minus negative 8. And I'm going to just move this up just a little bit. Now, remember, subtracting a negative is the equivalency of adding. So what we're technically doing is getting negative 9 and adding the fraction 123 divided by 7. And on the bottom, the same thing. Instead of subtracting a negative 8, we can just simply add a positive 8, since 2 negatives make a positive. So subtracting a negative is the equivalency of adding. Same thing down here. Subtracting a negative and a negative is the equivalency of adding. And again, if I take this one thing at a time, like the numerator, and I get negative 9 plus 123 over 7, that's equal to the fraction of 60 over 7. And well, negative 4 plus 8, that's equal to negative 4. So if I divide negative 60 over 7 and I divide it by negative 4, that's equal to negative 15 over 7. And this is your answer. And the last part of our review is identifying again the parent functions to these equations. So here, the parent function to this equation that looks like a snake right here is the cube root 1. So the original most basic function looks like this, which is the formula y is equal to x to the 3rd power. So you're just again identifying the parent function. I don't want you to come up with the equation to this graph. I just wanted you to identify if this is a transformation of the parent function, what is that parent function? So that would be this one right here. So by doing something to this equation is going to result to this graph here. But I don't want to know what that is. I just want to know the parent function. So like right here, looking at the characteristics of this one right here is the only one that has discontinuities, and that is your reciprocal function. So y is equal to 1 over x. And this is your square root function, or this is a transformation of the square root function, which is y is equal to the square root of x. So that's all you have to do for the last 3 problems. Just be able to identify what the parent function, the basic function, parent function to these graphs. And there you have it. If you have any questions, please do not hesitate to email me or send me a message or a reminder. I hope again this review was concise and thorough enough for you. But like I said, if you have any questions, contact me. Thank you again for watching, and I hope you have a great day.